this session we will be covering a complete graph, biparty graph and regular graph. So, complete graph, a simple graph of order n greater than or equal to 2 is said to be a complete graph if every vertex passes edges with all other vertices and is denoted by kn. Usually when we talk about a complete graph, so if we have a vertex, say I have a vertex here, this is k2, right. So, V1 and V2, two vertices, and when we have two vertices, these two vertices are connected, right. So, then I can call it as a K2. So, both the vertices are connected, right. Similarly, if I have three vertices, V1, V2 and V3. So, all the vertices are connected through the edges, right. So, here we have three edges. So, we call it as a K3. So, this is a complete graph. So, here if we have a single vertex, say, so here we do not have an edge. So, we do not consider K1 as a complete graph, right. So, that is why in the definition we tell that a simple graph of order n greater than or equal to 2 is said to be a complete graph. So, similarly K4, so here I have 4 vertices V1, V2, V3 and V4, right. So, all the vertices are interconnected. So, we call it as a complete graph of K4. So, complete graph with vertices 2, 3, 4 respectively are denoted here on the diagram, and Kuratowski first graph is called as K5. K5, if we have 5 vertices, so this we call it as a Kuratowski's complete graph K5. So, all vertices are connected, right, then we call it as a K5. So, these are some of the properties or the formulas that we are going to use in a complete graph. A complete graph K5 will have n choose 2 edges, right. So, based on the handshaking lemma or handshaking property. So, the degree of every vertex is equal to n minus 1. So, in a complete graph we have n minus 1 degree at each vertex, right. So, here next a complete graph with n vertices, namely Kn as 1 by 2 n into n minus 1 edges, as we have seen in the first statement, that is n choose 2 edges. So, if we have n vertices in complete graph, how many simple graphs can we have? We can have 2 to the power of e simple graph, right. So, the number of edges we can have is equal to n into d by 2, where d is the degree of every vertex, right. So, n into d by 2. So, if I, for example, if I consider with 3 vertices, right. So, n is equal to 3 and d is equal to 2, right. So, here each vertex has a degree 2, right. So, this vertex, if I call this as A, this vertex is having a degree 2, means the edges that are incident at this vertex is 2. So, I can call it as degree 2. Here also we have degree 2, here also we have degree 2. So, in general degree of this graph is 2, and here we have n is equal to 3. N is the number of vertices. So, n into d, that is 3 into 2 divided by 2. So, we get 3 edges. The number of edges will be equal to 3 here. So, next we have a biparty graph. A simple graph G is equal to V comma E with a vertex partition V can be divided into 2 independent sets, V1 and V2, and every edge of the graph connects one vertex in V1 to one vertex in V2. Then we call it as a biparty graph. So here in case of biparty graph, we divide the number of vertices into two sets and we try to connect. So here I have divided the given vertex into two sets. V1 is equal to V1 comma V4 and V2 is equal to V2, V3 and V5. So two sets I have. So V belongs to V1 comma V2, and if every edge of E joins the vertex in V1 to a vertex in V2, then we call it as a biparty graph. So here the diagram is, so V1 and V4, V1 and V4 they belong to one set, V2, V3, V5 belongs to another set. So now we are connecting from V1 set 1 to set 2, then we call it as a biparty graph. So here V1 is a subset, right, of the main vertices V, and V2 is also subset of V. V1 union V2 will be equal to V. V1 intersection V2 will be a null graph, right. So here V1, V1 and V4 belongs to one set, V2, V3, V5 belongs to another set, right, and V1, this entire thing we call it as a set V1, and this entire thing I call it as a set V2, right. So now V1, this is V1 is a subset of the entire set V, and V2, this is a subset of entire set V. Union of these two is nothing but V, and the intersection of V1 and V2 will be a null graph, right, that is a null set, right. So every edge in G, every edge in this graph joins a vertex in V1 and a vertex in V2. So then we call it as a biparty. Since as the name suggests, here biparty graph, so we are partitioning the given number of vertices into two sets. So complete biparty graph. A complete biparty graph is a graph where every vertex of the first set is connected to every vertex of its second set. So here this is called as a complete biparty graph. We have seen a complete graph where all the vertices are connected to all other vertices, then we call it as a complete graph. So here this is an example of a complete biparty graph where we have two set of vertices, V1 and V4 is one set, V2 and V3 is another set, and we have connected the elements of set 1 to the elements of set 2 and all other vertices. See here V1 belongs to set 1 and it is connected to all the vertices of set 2. V4 belongs to set 1 and it is connected to all other vertices of set 2. So we call it as a complete biparty graph. So how many edges are there in K, R, comma, S? So what is this K, R, comma, S? K, R, comma, S, K is used to refer the complete graph, and R, comma, S, R belongs to the first set and S belongs to the second set. So a biparty graph is identified as R, S, comma, K, R, comma, S. So here K, R, comma, S is equal to K, 2, comma, 2. And here in this case the number of edges will be equal to, so the number 2 into 2, that is equal to 4, and for example if I consider K 3, comma, 2, right, so it is equal to 3 into 2, that is equal to 6. So the maximum number of edges in a biparty graph with n vertices is given by n square by 4. The number of edges will be equal to n square by 4. So here if I take n is equal to 4, so we will have 16 by 4, that is equal to 6 edges. A complete biparty graph has R plus S vertices and R into S edges, A complete biparty graph will have R plus S vertices and R into S edges. So, some special cases of a biparty graph. So, here we have star graph, a complete biparty graph of the form K 1 comma S minus 1, that is we will have 1 vertices in one set and n minus 1 vertices in another set, then we call it as a star graph and it is represented like this, right. So, V1 comma V2, that is n is equal to 2 comma K 1 comma 1. So, V1, this is the set V1 and here we have V2, V3, V4. So, this represents the star graph. Then we have one more special case in complete biparty graph, Kuratov-Vasky's second graph. So, Kuratov-Vasky's first graph was a complete graph with K5 and Kuratov-Vasky's second graph a complete biparty graph of the form K R comma S having R is equal to S is equal to 3. Symbolically represented by K3 comma 3 is called as Kuratov-Vasky's second graph, which is of the order number of vertices will be equal to 6 and the number of edges will be equal to 9. So, this graph we represent it, we call it as a Kuratov-Vasky's second graph. So, next is in a biparty graph there are no odd cycles, right. So, if your biparty graph has even number of edges, then we will have a cycle, whereas if we have odd number of if we have even number of vertices, then we will have a cycle, but if we have odd number of vertices, then we will not have a cycle, right. So, here we can form a cycle V1 V1 to V2, then V3, we can move like this, right, and here and we can go here, right. We can form a cycle, but if we have an odd number of vertices, right, then we will not have a cycle. Cycle cannot be formed with the odd number of vertices. Then complement of a biparty graph. So, we know that this is a biparty graph where we are connecting all the vertices from one set to all the vertices in another set. So, what will be the complement of a biparty graph? Complement of a biparty graph will be two disjoint sets. That is we will have two subgraphs. So, one subgraph which belongs to set 1 and the other graph which belongs to set 2, right. So, V1, V3, V4 belongs to one set and V2 and V4 belongs to another set. So, this is about biparty graph. Next we are moving towards a regular graph. A regular graph G which has all its vertices of the same degree, say R, then we call it as a regular graph. So, here I have taken an example of 3 vertices, right, and all the vertices are interconnected. So, here the vertex of V1 is having a degree 2, vertex V3 is also having a degree 2 and vertex V2 is having a degree 2, right. So, here since all the vertices are having same degree, then we call it as a regular graph. Isolated vertex having 0 degree, pendant vertex will be having a degree 1, but here in a regular graph we need to have all the vertices same degree, then we call it as a regular graph. So, let us see what is the difference between a complete graph and a regular graph. So, we know that in a complete graph, a simple graph of order n greater than or equal to 2 is said to be a complete graph, right. So, in case of a complete graph, we have n choose 2 edges, right, and each node will have a degree n minus 1. Whereas, in case of regular graph, a graph which has all its vertices of the same degree is said to be a regular graph. So, the number of edges are given by n into d divided by 2. So, here is an example of a complete graph K2 since in case of complete graph we consider n greater than or equal to 2, right. So, I have taken 2 vertices. So, this is a complete graph. Similarly, for K3 I can call it as a complete graph, right. So, now when I take K4, right, K4, here I have 4 vertices, but this is not a complete graph because we have not connected a u2x and v2w. So, it is not a complete graph, but it is a regular graph because all vertices are having same degree, that is 2, right. So, this is a complete, this is not a complete graph but a regular graph, whereas the other two graphs K2 and K3 are a complete graph.